Welcome to visual engineering, where complex ideas become easy to understand through immersive visual breakdowns. If you enjoy visual explanations of AI, software engineering, and cutting-edge technology, consider subscribing, and let's begin.
In the simplest form of computing, data lives on a single server. When a user queries a record or makes an update, they communicate with this singular ledger. There is no ambiguity. Consistency is effortless because there is only one version of reality. But a single machine is bound by its physical hardware. As an application scales from a few hundred users to millions of concurrent requests, that single source of truth becomes a bottleneck. The central processor in memory can only execute so many read and write commands per second. When that physical capacity is overwhelmed, the server fails. The database stops responding, and the entire application goes offline. Perfect consistency has no value if the system cannot stay online. To survive at a global scale, the architecture must change. To solve immense volume requires horizontal scaling. Instead of attempting to build one impossibly large server, engineers duplicate the primary database into multiple identical replicas. The system reroutes incoming traffic across these new machines, ensuring high availability. But this introduces a mechanical problem. When a user updates a record, the write lands on just one replica. A split second later, a second user pulls a record from a different replica. They receive stale, outdated information. By distributing hardware to keep the service online, engineers effectively destroyed the single source of truth. The system now holds multiple, conflicting versions of reality. To synchronize those conflicting versions, replicas must transmit data over physical fiber optic cables. Even moving at the speed of light, electrons take time to travel across a continent or an ocean. A signal traveling from a data center in New York to one in Tokyo requires about 200 milliseconds. That travel time creates the inconsistency window, a brief, inescapable period where geographic distance ensures two servers hold different data. Worse than latency is a total physical disconnection. Construction equipment cuts a trench, or a network switch fails, and the cable severs entirely. This creates a network partition, isolating a portion of the database replicas from the rest. This forces a mechanical choice. If a user tries to save their data to one of these isolated nodes, the system must decide whether to accept the update, knowing it cannot share it with the others, or reject the update entirely. Operating across massive physical distances means network partitions and temporary data divergence are not rare anomalies. They are statistical certainties. To manage this uncertainty, the system relies on distributed consensus. This is a mathematical framework that allows disconnected, independent nodes to agree on a single truth without needing a central coordinator to dictate it. It works through a concept called a quorum. The system defines the total number of nodes, designated as n. It then sets a specific number of nodes required to confirm a read operation, r, and a number required to confirm a write operation, w. As long as the sum of the read nodes and write nodes is strictly greater than the total number of nodes, the system forces an overlap. The cluster is mathematically guaranteed to query at least one node that holds the most recently written data. Many architectures organize this process using a leader-follower model. The nodes elect a single leader to serialize incoming write commands, ensuring all updates are placed in a strict chronological order before propagating to the followers. In this distributed environment, the concept of immediate, absolute truth is discarded. It is replaced by mathematical probability and majority rule. These mechanical rules are formalized in distributed computing by the CAP theorem. It states that any distributed data store can provide only two of three guarantees: consistency, availability, and partition tolerance. This table outlines the resulting design rules. Because network partitions are a physical reality that cannot be avoided, partition tolerance is mandatory. Therefore, when a network fails, architects are forced to make a strict choice between maintaining consistency or maintaining availability. If a system handles bank transfers, it chooses strong consistency. During a network failure, it will completely block user requests to prevent money from being double spent. It trades uptime to guarantee accuracy. Contrast that with an e-commerce platform during Black Friday. If a network link drops, the platform must allow customers to continue adding items to their shopping cart. It chooses availability, allowing the inventory counters to be temporarily wrong. Eventual consistency is a deliberate, strategic business decision. The organization calculates that keeping the service online and processing revenue is more valuable than maintaining perfectly synchronized data at every given millisecond. Architectures like Apache Cassandra and Amazon DynamoDB are specifically built for this highly available, eventually consistent reality. They are designed to absorb massive traffic spikes and tolerate widespread node failures without ever dropping user requests. Conversely, Google Spanner takes a radically different path. It attempts to enforce global strong consistency across massive geographic distances without sacrificing scalability. It achieves this through TrueTime, an API backed by physical atomic clocks and GPS receivers bolted into the data centers. By relying on highly precise timekeeping hardware, the system enforces a strict global chronological order for every transaction. The evolution of database architecture is a progression from a simple single server through the mechanical complications of replication and network latency, and finally into the mathematics of consensus protocols. Modern distributed software does not defeat the limits of physical hardware or the speed of light. It simply masters the art of the engineering trade-off.
Thanks for watching. Subscribe for more visual breakdowns of AI, software engineering, and technology. See you next time.